Let's get right into it. Number 6. The Scotch tape miracle. Imagine you're in your kitchen, messing with a pencil, and you accidentally create a Nobel Prize, and also kind of bully a major physics theorem on the way out. That's basically what happened with graphene. For decades, solid-state physics had this stern, rules-lawyer vibe about ultra-thin materials. There's a famous idea called the Merman-Wagner theorem that in simple terms suggests a truly 2D crystal, like 1 atom thick, shouldn't be stable. Thermal vibrations should make it fall apart. The universe is basically saying, nice try, paper-thin materials, not on my watch. And then 2 researchers, Andrei Geim and Konstantin Novoselov at the University of Manchester, looked at that rule and went, okay, but what if we use Scotch tape? Not a clean room. Not a billion-dollar machine. Clear tape you could buy for around $2. Here's the move. You take a chunk of graphite, yes, the stuff inside your pencil stick taped to it, peel it off, fold it, peel it again, and repeat. Over and over, like you're stubbornly trying to remove lint from the world's dirtiest sweater. Each peel makes the flakes thinner, until eventually you've got a sheet that's literally 1 carbon atom thick. Congrats! You just made graphene, in the most disrespectful way possible. And the wild part? It didn't self-destruct. It sat there at room temperature like, yeah, I'm fine. Turns out graphene is a single layer of carbon atoms arranged in a hexagonal honeycomb pattern. Those carbon-carbon bonds are insanely strong, and instead of tearing apart from thermal jitter, the sheet can flex and ripple. Think of it like a trampoline. You don't fight the bounce by being rigid, you absorb it by waving a little. That rippling is part of how it stays stable instead of snapping. The payoff is ridiculous. Graphene is 1 atom thick, reportedly about 200 times stronger than steel, and it conducts electricity better than copper. It's the kind of material that makes engineers start whispering future like it's a prayer. It's being explored for things like fast-charging batteries, phone heat spreaders, and even coatings that help fight rust. Of course, there's a catch. Making perfect graphene at massive industrial scale without defects is still a headache. But the core irony doesn't change. A complicated physics limitation got embarrassed by office supply tape. In 2010, Geim and Novoselov won the Nobel Prize in Physics for it, which is just beautiful. Somewhere, a theoretical physicist is still trying to process the fact that a $2 roll of tape walked into the room and said, "Your theorem? Cute." Number 5. Sonoluminescence. Back in 1934 in Germany, researchers Hermann Frenzel and H. Schultes were messing around with sonar experiments and accidentally found something that sounds like a prank the universe pulled on physics. Because somehow, with sound waves and water, you can get a tiny flash of light like a microscopic star trapped in a jar. Here's why that's so wrong. Sound is usually the gentle kind of energy. It wiggles air, it rattles windows, it puts you to sleep on long car rides. Meanwhile, intense light and crazy heat are supposed to come from chemical reactions, or nuclear reactions, or at least something dramatic enough to justify the drama. And then sonoluminescence shows up like, nah, try a speaker. The setup is deceptively simple. You drive sound into water at the right frequency, and you create bubbles, tiny pockets of gas. Those bubbles grow, and then the sound pressure slams them back down, hard. Like, violently. The bubble collapses so fast, it's basically a microscopic implosion. And that collapse is where the magic turns into a fist fight. According to reports, the bubble shrinks down to around a micrometer, and the collapse creates a shock wave inside the bubble. The gas gets compressed so intensely that the temperature spikes into the tens of thousands. Estimates put it around 20,000 Kelvin, about 35,000 degrees Fahrenheit. That's surface of the sun territory, except it's happening inside a bubble you could never see without help. Then flash, a burst of light so quick it's almost rude. The flashes last something like 35 to 100 picoseconds, not milliseconds, picoseconds. That's not a blink. That's not even the idea of a blink. That's the universe tapping you on the shoulder and vanishing. In 1989, Felipe Gaitan helped push this into a cleaner, more controlled version, what's called single bubble sonoluminescence. One bubble, one captive little doom balloon. Repeated flashes, like you've got a tiny light bulb powered by pure, angry pressure. The problem is, classical physics really doesn't like explaining this. Because the energy input looks so normal, just mechanical vibration, and the output looks totally unhinged light and extreme heat, it's the worst kind of conversion chart, the kind that makes your professor rub their temples and pretend they didn't see it. If you need a mental picture, it's like clapping your hands underwater, except the clap is so insanely concentrated it makes the water spark. Obviously, you're not actually doing this in your pool unless you want to become a cautionary tale, but that's the vibe. A weak-looking push, focused so tightly it turns into a tiny, violent furnace. And yes, for a while, people got excited and started whispering cold fusion. The idea was basically, if it gets that hot, can it trigger nuclear reactions? But that claim is disputed, and the general takeaway is, it's not strong or sustained enough to keep a nuclear reaction going like that. Still, it's not just a science party trick. The same underlying idea, acoustic cavitation, is used in real-world ways. In medicine, it's tied to techniques that can break up kidney stones, and it's been explored for things like cleaning or disinfecting water by wrecking bacteria with extreme local conditions. So yeah, sound, the thing you use to lull babies to sleep, the thing you put on to relax. Turns out if you crank it the right way, it can also be the match that lights a star inside a collapsing bubble of water. Physics is beautiful, and occasionally, it's also completely unhinged. Number 4. The oh my god particle. Everyone thinks the universe has speed limits. Like, sure, you can go fast, but if you go too fast for too long, space itself starts slapping energy out of you. That's the whole idea behind the GZK limit basically, a cosmic slow-down rule for ultra-high energy particles traveling across the universe. And then in 1991, something showed up over Utah and basically said, cool story, watch this. On the 15th of October 1991, the University of Utah's Fly's Eye cosmic ray detector picked up a signal so extreme the team assumed the equipment had glitched, because what they saw looked illegal. A single particle, basically one proton, hit Earth's atmosphere carrying about 320 eV of energy. That's roughly 6 times higher than what the GZK limit says should survive a long trip through space. Here's why that's so disgusting. The universe is filled with the leftover radiation from the Big Bang, the cosmic microwave background. And if a particle is traveling with absurd energy for long distances, it should smack into that background, bleed energy, and drop back down below the cutoff. That's the toll road the universe charges. You can't dodge it. That's the whole point. Except, apparently you can. At least once. To make the energy feel real, researchers used a comparison that sounds like a joke until you remember it's one particle. It's like a baseball moving around 60 miles per hour, except all that kinetic energy is crammed into something far smaller than an atom. It's not just fast, it's concentrated violence in proton form. And when they ran the numbers, it got even crazier. This thing was traveling at something like 100.0% the speed of light, basically c, with an absurd amount of nines behind it. Close enough that the difference is almost philosophical. That's why it got the name. Not specimen UHECR 199111015. Not event 6. They called it the oh my god particle because that's the sound your brain makes when physics politely asks for a receipt and you realize you don't have one. So what was it? In technical terms, it's an ultra-high energy cosmic ray UHECR. In human terms, it's a bullet fired by the universe. The leading guesses are the usual heavyweight suspects. Maybe it got accelerated by something like a supermassive black hole or some extreme cosmic environment we barely understand. But here's the caveat. Its true origin is still a mystery. Nobody has a neat, satisfying answer for what kind of natural particle accelerator can crank a proton up to that energy and still deliver it to Earth intact. Which is why this single event mattered. It forced astrophysicists to start inventing new theories, because the old ones were suddenly looking a little optimistic. And it didn't stop there. This kind of rule-breaking particle is a big reason humans built gigantic observatories to hunt for more like the Pierre Auger Observatory in Argentina. Because once you've seen one cosmic speeder blow through the checkpoint, you start watching the highway a lot more closely. Punchline? The GZK limit is basically the universe's speed trap space itself running radar. And the oh my god particle? It didn't just speed. It drove a supercar straight through the toll booth and kept going. Number 3. The one-sided magnet. This is basically a magnet that forgot to bring its other half, which, according to every physics class you've ever taken, should be impossible. Because here's the rule. Magnets are dipoles. North and south always as a pair. Cut a magnet in half? Congrats! You now have 2 smaller magnets, each with its own north and south. You can keep chopping forever, and you will never get a lonely north-only magnet. Maxwell's equations laid down back in 1873 are basically yelling, "Stop trying! Monopoles don't exist!" And then, about 150 years later, scientists said, okay, but what if we cheat using extreme cold and a very weird crystal? Enter spin ice. Spin ice is a material. One famous version involves dysprosium titanate, where the atoms sit in a geometric arrangement that's kind of a trap. The structure is built like a little network of tetrahedra, and when you cool it down to near absolute zero, reportedly around 0.6 to 2 Kelvin, the magnetic moments inside get stuck in a frustrated state. And frustrated in physics doesn't mean annoyed. It means the geometry literally won't allow everything to settle into the nice, lowest energy arrangement it wants. The system can't relax normally. It's like trying to seat a group of people at a dinner table where every chair is somehow the wrong chair. So the material looks ordered, but it's secretly under tension. And when that tension snaps in a certain way, something insane happens. Instead of the magnetism breaking into clean north-south pairs like it should, the north and south ends can separate inside the crystal. Not as free fundamental particles flying around the universe, but as emergent quasi-particles that behave like magnetic charges moving independently through the material. Meaning, for the first time, humans could observe something that acts like a magnetic monopole, an isolated north here, an isolated south there traveling separately, at sub-nanometer scales, inside this icy little magnetic maze. In 2008, researchers like Claudio Castelnuovo, Roderich Moesner, and Shivaji Sondhi argued this could happen, and by 2009, experiments backed it up. Inside spin ice, you can get these one-sided magnet behaviors that look like monopoles, connected by what's often described as Dirac string-like patterns through the material. Here's the cleanest analogy. A pair of scissors always has two blades, right? You can't have one-blade scissors, but imagine you build a machine that creates a floating shadow of one blade, and that shadow can actually cut paper. That's what's happening here. Maxwell is still right about nature in general, but inside this special material, the system creates a working illusion that behaves like the forbidden thing. And there's an important caveat. This isn't the fundamental monopole Paul Dirac predicted in 1931, just cruising through space like a mythical Pokemon. This is an emergent monopole, something that only exists as a collective effect inside the crystal's rules. But even as a fake monopole, it's a big deal. Because if you can move magnetic charges around like electrons, you can imagine magnetricity, a magnetic current where information and energy are carried in new ways. In theory, that could lead to cooler, more efficient data storage and devices that waste far less energy than what we're stuck with now. So yeah, Maxwell didn't get dunked on by nature, he got dunked on by humans building labs cold enough to make the universe reveal its loopholes. Number 2, the nothingness force. So why don't we just use empty space as free energy? Because empty space is not empty, and it's also kind of a bully. Classical physics sells you this comforting idea that a perfect vacuum is literally nothing. No matter, no energy, no anything. Just pure zero. Like 0 plus 0 equals 0. End of story. Quantum mechanics walks in and goes, yeah, about that. Because in the quantum world, there's basically no such thing as truly empty space. Even in a vacuum, the field still jitters. Energy still fluctuates. Little virtual particles pop in and out of existence for absurdly tiny slices of time zeptosecond-type vibes. The void isn't calm, it's boiling. In 1948, a physicist named Hendrik Casimir at Philips Research Labs realized something terrifying. If that background quantum noise is real, it should be able to push on stuff. His idea was simple and unhinged. Take two ultra-thin metal plates. Keep them uncharged, neutral, perfectly parallel. Put them in a vacuum. Bring them insanely close, like within about a micrometer, or even tighter. And then, the plates should pull together. Not because of magnets, not because of static electricity, not because of gravity, just because of nothing. That sounds like science fiction. Where is the force coming from if the space between them is empty? Here's how it works. The vacuum isn't empty, it's full of fluctuating fields, which you can think of like waves of possible energy. Outside the plates, there's plenty of room for lots of wavelengths to exist. Between the plates, the gap is so tiny that many wavelengths physically can't fit. So fewer vacuum modes exist in the gap than outside it. That creates a pressure difference. More quantum push from the outside, less from the inside. And the result is a net force squeezing the plates together. If you need a normal person image, picture two ships parked side by side in choppy water. The ocean outside is pounding their hulls with waves, but the narrow water channel between them is relatively calm. The wave pressure from the outside ends up nudging the ships into each other. Same concept, except the waves are quantum fluctuations and the ocean is nothing. For decades, this lived in the category of cool theory. Then, in 1997, Steve Lamoureux at the University of Washington measured the Casimir force in a lab, in the submicrometer range, basically confirming Casimir wasn't just philosophizing. The vacuum really can produce a measurable force. And the numbers get spicy when the gap gets tiny. At around 10 nanometers, the force can be roughly comparable to 1 atmosphere of pressure. Which is wild, because you're talking about a force generated by what you'd swear is empty space. Now, huge caveat. This does not mean you can build a perpetual motion machine, or a vacuum engine, or levitate your car like a TikTok conspiracy thread. In everyday life, the force is unbelievably small unless you're at microscopic distances, with carefully controlled surfaces. But at the nanoscale, it's a real problem. In micro and nano machines like MEMS components, parts can get so close they literally stick together and fail. The Casimir effect becomes this invisible enemy that turns tiny moving parts into a glued-together paperweight. So yeah, science spent an absurd amount of effort proving something philosophers have argued about forever. Nothingness isn't weightless. Sometimes, the emptiest part of the universe is the thing doing the squeezing. Number 1. The backwards liquid. One day, physicists asked a question that sounds like a dumb shower thought, and then they actually built the answer. What happens if mass is negative? Because in your world, Newton's second law is basically sacred. Force equals mass times acceleration. F equals ma. You push a shopping cart forward, it accelerates forward. Mass is positive. Reality stays polite. But in 2017, a team at Washington State University researchers, like Peter Engels and Michael Forbes, created a fluid that behaves like it has negative mass. Meaning, when you push it forward, it accelerates backward, toward you, like the universe just flipped the controls. Here's how they did it without accidentally summoning a black hole in the lab. They started with rubidium atoms and cooled them to a tiny fraction above absolute zero, until the atoms merged into a single quantum state called a Bose-Einstein condensate. A BEC is basically matter in cheat code mode. Everything moves together, and quantum rules stop hiding in the background. Then they use lasers to set up something called spin-orbit coupling, which is a fancy way of saying they force the atoms into a weird relationship between how they move and their internal state. The atoms get trapped on a strange energy curve, where the usual push equals go that way logic can break. And then came the moment of truth. They hit this ultra-cold clump around 100,000 rubidium atoms with another laser kick, trying to shove it out of its trap. If it were normal matter, it would fly away like a ball getting punted. Instead, the cloud absorbed the push and accelerated back toward the laser, toward the thing pushing it. It acted exactly like it had negative effective mass. If you need an everyday analogy, imagine you lean into a door to push it open, and the door responds by swinging the other way and smacking you in the forehead. You didn't pull it, you pushed it. And it still came at you. That's the vibe. So what's actually happening? At the quantum level, particles don't have the simple, straight-line relationship between energy and momentum that you're used to. In this engineered setup, the atoms get forced onto a part of their dispersion curve, the energy versus momentum slope that bends the wrong way. That bend flips the sign of the effective mass. So when you apply force, the acceleration points opposite the force. It's not magic, it's math, trapped in the weirdest possible corner. Now, giant caveat. This is effective mass, not gravitational mass. It's not anti-gravity goo. If you drop it, it doesn't fall upward into the ceiling like a cursed helium balloon. The negative part is how it responds dynamically inside the laser-shaped environment. But even as a controlled lab phenomenon, it's huge. It gives scientists a way to simulate extreme physics stuff we can't easily poke in real life, like the strange behavior inside neutron stars, near black holes, or in theories about exotic matter. Basically, you can study impossible cosmic conditions without leaving Earth. And the punchline is just mean. Earth might be the only place in the universe where you punch something, and its face accelerates into your fist harder. Newton wrote the rules. Quantum physics keeps finding loopholes. That's all for today. I'll be making similar videos in the future. Subscribe to see them.